So I'm audible, right? No, to them. Okay. So good afternoon, everyone. I think I'm audible to all of you. So I'll take up some questions. Where will I see questions if they ask? Okay. Yeah. So good afternoon, everyone. So I have a few questions. Yeah. So I'll just. So I have few questions already asked by a participant. So I'll take those questions first, one by one. And in case you have any questions, you can type those in the chat box. And once I finish taking up the questions which were already asked, so I'll then go to this one, question which are asked in the chat box. So let me just. So, okay, so screen is already shared. Okay. Yeah. So the first question that was asked is from a previous year assignment. So that is from year 2021. Okay. So assignment 5. Okay. So the questions are from question 1 to question 4 and question 9 to question 10. Okay. So let me just write those questions over here because others may not have access to those questions. So question 1 to 4 last year was for the motion of a continuum body, the material description, the deformation mapping was given in this particular form. B of t x1 minus b2t x2 x2 equal to b1t x1 plus b2t x2 and x3 was capital X3, where b1t was nothing but e raised to power t and b2 so b2t was e raised to power minus t. And you're also given in this question the velocity and acceleration were given to be v1, v2, v3. Acceleration was a1, comma a2, comma a3. And then for a particle which is currently particle A, which is currently located at 4, 5, 0, you have to find out the velocity and acceleration at time t equal to 1. So at time t equal to 1, the particle is at this particular position. So the question is, how do you find the velocities and acceleration? So the solution to this is, so you would know that the velocity is nothing but the partial derivative of the material, the spatial coordinates with respect to the time. So which means it would be del x1 by del t, del x2 by del t, and del x3 by del t. And therefore, you've been given x1, x2, x3 here in terms of capital X1, capital X2, capital X3, which are the material coordinates. So these material coordinates are basically all the material coordinates are fixed, so they are not dependent on time. However, B1 and B2, they are dependent on time. So what you have to do is first take the time derivative of these quantities. So if you see del x1 by del x2, let me go to the solution. So del x1 by del x2 will come out to be e raised power tx1. Okay, so this is e raised power tx1 plus e raised power minus tx2. So that is your del x1 by del t. So del x2 by del t. So you take the partial derivative of the spatial coordinate x2 with respect to time. So you will get this as e raised power t x1 minus e raised to minus tx1. Okay. And then what you have to do is basically, sorry, x2. And then del x3 by del t basically is equal to 0. So now, knowing the time t, we know time is 1 second. However, we do not know what is x1, x2, and basically we don't need x3. So these spatial positions of particle A are currently given to us at time t equal to 1. However, we don't know its material position. Okay, so what we have to do now is, okay, we can go to the next slide. So I can use the deformation mapping and I can see that x equal to 4 at t equal to 1, which implies that from the first equation of the deformation mapping, 4 equal to e raised power 1, e x1 minus e raised to minus 1 x2, x equal to 5 at t equal to 1. So from the second equation, we have e raised power x1 plus e raised power minus 1 x2, and then x equal to 0 at t equal to 1, which implies 0 equal to x3. So solving that, you'll get the material coordinate x1 as 9 by 2e, x2 as e by 2. Okay, so it will not be here. Okay, let me see if I can. Okay, okay. Okay. And then capital X3 will be anyway equal to 0. Okay. So now you know capital X1, capital X2, and capital X3. So now you can go back here. So you can substitute in this equation t equal to 1, x1 equal to 9 by 2e, x2 equal to e by 2. Here also you can substitute x1 as 9 by 2e, x2 as e by 2, and then if you go here, what you can do is you can solve for that. So velocity v1 will be 9 by 2e plus 1 by e. So 9 by 2e into e plus 1 by e into e by 2. So e gets cancelled out. So you have 10 by 2, which is equal to 5. That is the answer. So v2 is e times 9 by 2e. Okay. Minus 1 by e into e by 2. Okay, so you'll get what is called the 8 by 2, which is equal to 4. And anyway, v3 is equal to 0. So this is how you can solve for the velocity. So I guess this is clear. Is this clear? Let me go to the chat box. Yeah. If there is any question in this solution, you can ask right now. Is it clear? I mean, if you can type yes or no, then I can know because I cannot hear anybody. Okay. So now on the similar lines, you can calculate basically the accelerations. Okay. So now you can calculate acceleration. So acceleration is nothing but del V by del T. Okay. So which is del V1 by del T, del V2 by del T, del V3 by del T. And now from our previous solution, we know what are the expressions for V1, V2, and V3. So we already have it in terms of the time and material coordinates x1, x2, x3. So again, we can take the derivative with respect to time t. So this will come out to be e raised power tx1 minus e raised power minus tx2. So that's your acceleration a1. So this is e raised power x1 minus x2 and comma 0. Okay. And now following the similar procedure, now we know x1, x2. Okay. So x1 is 9 by 2e. So this is 9 by 2e. X2 is e by 2. Therefore, we can basically solve for acceleration. So your accelerations will come out to be 4, 5, 0. So this, I guess, I don't have to work it out. You can work it yourself. Okay. So is it clear?
Yes, sir.
Yeah. Okay. Okay. So now I'll go to question 9 and 10 of assignment 5, which was asked. Okay. So this is a bit lengthy. I will basically first go to the slide. Okay. So now what I'll do is this is question 9 and question 10 of assignment 5, 2021, last year assignment 5. And what this question asked, let me revise, let me detail out the question. So the question said that it can be shown that for the case of 2 dimensions, the polar decomposition, so you know polar decomposition, F equal to RU. Okay, so R is your orthogonal tensor, U is the your right stretch tensor. So so here U can be expressed as, and here there was a typing mistake. So let me correct. So there was this brackets were missing in the original assignment. So the question says that the U can be written as the first invariant of the right Cauchy-Green tensor plus a constant A times the Jacobian corresponding to right Cauchy-Green tensor raised to power minus 1 by 2 times C plus a constant B times Jacobian corresponding to C times second order identity tensor I. Okay. So where I1 is the first invariant, J is the third invariant, which is also given by C11, C22 raised to power 1 by 2. So now A and B are some numeric values which have to be found out. So basically you have to derive the relation. You have to show that U is in this form, and from the form that you'll derive, you'll be able to get what is the value of A and B. Okay. So what we first have to do is, so in 2 dimensions, okay, let me write. So you can write the characteristic polynomial. Characteristic polynomial of U as a quadratic equation in its eigenvalue lambda, that is lambda alpha square minus the first invariant of u times lambda plus the third invariant of u times 1 equal to 0, where this alpha and there are two eigenvalues, so alpha equal to 1 and 2. Okay, so now I1 is trace of u and j here, j of u is basically, so this is I1, j here is determinant of u. Okay, so now what we have to do is we recall the Cayley-Hamilton theorem. So I guess you know what is meant by Cayley-Hamilton theorem. So every matrix or a second order tensor will satisfy its own characteristic equation. Okay, so that's what Cayley-Hamilton theorem states. So using that, I can write. So if I substitute u, let me go back. Let me write this as equation 1. So substituting u in equation 1, I can get u square minus I1 of first invariant of u times u plus the third invariant of u times the identity tensor equal to 0. Okay, so 0, the second order tensor 0. Okay, once you have that, now you know that u square equal to c. Okay, so if you substitute u square equal to c over here, and then you can solve for u. Okay, so from this equation, you can solve for this u, and that should come out to be 1 upon the first invariant of u times c plus the third invariant of u times identity tensor. Let this be equation 2. Okay, now I can take trace of equation 2. So trace of u equal to 1 upon I1 u, and this is nothing but I1 u itself. Trace of c plus j of u times trace of I. Now in 2 dimensions, trace of I is equal to 2. Okay, so this is 2. Now from here, so I can get my I1 square u as trace of c, which is nothing but the first invariant of c plus twice of j of u. Okay, so then I1 will become 1 by 2. Okay, square root of this quantity, and this I can substitute here. Okay, so to get the value of u in terms of the first invariant of c. Okay, now what I can do is I can find out the relation between, so u is equal to u square equal to c, therefore determinant of c equal to determinant of u the whole square. Okay, so I can show that j of u equal to j of c. So this I leave. So once you get j of u as j of c, you can substitute j of u as j of c here, and also j of u as j of c here. And then you will finally arrive at your relation. So this I'm leaving, I mean, you can work out. So this is I1C plus 2J C 1 by 2 times C plus, okay, so this is, sorry, this is J times C into I. Now, if you compare with this relation over here, you will see that A is equal to 2 and the coefficient of B here, okay, so the coefficient of B here in this equation comes out to be equal to 1. So the answer is A equal to 2 and B equal to 1. Okay. So let me go back. Yeah. So is it clear?
Yes, sir.
Okay. Okay. So now I'll go to the assignments of the current year. So there is this question. Oh no, there is assignment 6. Yes, assignment 6, question 7 to 11. Okay. Okay. This also will take it up. Okay. So the next question is from MOOCs course 2021, assignment 6, question 7 to question 11. Okay, so let me read out the questions for everyone. So the state of stress at a point in a deformable body is given by sigma equal to 6, 4, 2, 4, 4, 2, 2, 2, minus 2. Okay. And then also, so you have a body. Okay. And at any point P, the state of stress is given by this second order tensor. And also at point P, there is a plane. Okay. At point P, you have a plane f of x1, x2, x3. And also again, there is one typo in this question. I think last year it was improved. So this is x1 plus 2x2 plus 3x3 minus 6. Okay. So there is a plane f x1, x2, x3, which passes through P, and the equation of that plane is given by following equation. So then what we have to find out is the, so we have to find out the maximum and minimum value of the principal stresses up to the 2 decimal points. We have to find out the magnitude of the stress vector. Okay, so magnitude of the stress vector which passes through point P. And then magnitude of the, we have to find out the magnitude of the normal stress vector which passes through P. And also, I think the magnitude of the shear stress, okay, which passes through P. Okay. So from Cauchy's rule, okay. So you know Cauchy's rule? Yeah. So using Cauchy's rule, what you can do is you can, at a point P, if a normal is known, okay, and the state of stress is given to you, so you can find out the stress vector at point P corresponding to this normal n, okay, using this rule. So now we know sigma, which is given to us. So this quantity over here is given to us. We need to first find out n. Okay. So for finding out n, we need the equation of the surface at point P, which is given to us. So n is the normal, and that's the unit normal. So we have to find out the gradient of f. So this is f. So you have to find the gradient of f and then divide it by the magnitude of the gradient. Okay, so that's a very trivial exercise. So that would be 1, 2, 3 divided by square root of 1 plus 4 plus 9, which is 14. So this is 1, comma 2, comma 3 divided by 14. So that would be the x1, x2, x3 component of the normal. So once you have found out the normal, you can find out the traction vector, okay, or the stress vector. So you know n, you know sigma over here. Therefore, you can find out t. Okay. Sorry. T is a vector. Okay. So now once you have found out the vector, okay, let me go to the next slide. So at a point P, once you have found out the, so this is the normal. Okay. You have found out the stress vector passing at point P, where the normal is n. So now you can project this. So this is your normal stress and this is your shear stress. Okay. So from vectors, we know that T equal to Tn plus Ts. And now Tn, so you have to take the projection of this vector on the normal. So that would be, so Tn will be nothing but the magnitude times the unit vector in this direction. So unit vector is nothing but n, and the magnitude of Tn will be nothing but T dot n. Okay, so you have to basically project this vector onto along the normal direction n. Okay, so this is the magnitude. So this becomes the magnitude and the unit vector is n. Okay, so using this, so we already have found out T, n we have already found out. We can calculate the normal stress vector, and then we can take the norm to find out the solution for the magnitude of the normal stress vector. So now from this equation, the shear stress is T minus Tn. So we already have calculated Tn from here. T is already calculated. So we can just simply take out the difference of the stress vector minus the normal stress vector, and we can get the shear stress. Okay, and then we can find out the norm to get the magnitude of the shear stress vector. Okay, so is it clear?
Yes, sir.
Okay, okay. So now I think there are no more doubts. So we'll move to, let me check the chat box. Okay, so there are no questions. So now there are a few questions from the current year assignment. Okay, so assignment 3, question 5 to question 6. Is it clear? I mean, is it right? Question 5 to question 6? Assignment
Yes,
3? Okay. Yeah, so what we have been given actually is Q equal to minus K gradient of theta. Okay, so you can write this as minus K del theta by del x1 E1 plus del theta by del x2 E2 plus del theta by del x3 E3. You just need to first take out the gradient. Okay, so now theta is given to you 2x1 square plus 2x2 square. So del theta by del x1 will become 4x1 and del theta by del x2 will become 4x2. Okay. Now question 5 says that K is equal to 1 by root 2. So what will be the coefficient of the heat flux vector? So Q is A1 E1 plus A2 E2. Okay. So if you substitute 4x1, 4x2 here, so del theta by del x3, sorry, that should be equal to 0. So Q comes out to be minus K times 4x1 E1 plus 4x2 E2 plus 0. Okay. So 0 times E3. So this is 0. So now K is 1 by root 2. So we can substitute 1 by root 2 here. And also in question 5, we are given x1 is 1 by root 2. X2 is 1 by root 2. So then Q will become minus 1 by root 2 times 4 into 1 by root 2 E1 plus 4 into 1 by root 2 E2. So if you open up the bracket, Q will be equal to, so root 2 is 2, and then 4 divided by 2 is minus 2 E1. And then this is root 2, 2, and 4 divided by 2 is 2, so 4E2. Now if I compare this relation and this relation over here, I get A1 equal to minus 2 and A2 equal to 2. Okay. So this is the solution for question 5, and this is the solution for question 6. So is it clear? Hello.
But during the assessment, it is given that the accepted answer is minus for A2.
Oh, no. This is minus. Sorry, this is minus. So this also is minus. Okay. Is it clear? Both are minus. See this, when you bracket, open up this bracket, both are positive inside the bracket. So this will be minus only. So A1 will be minus 2, A2 will be minus 2. Is it clear? Hello.
Yes, sir.
Yeah, so this is the solution.
Yeah.
Okay. So now I'll go to the next question, which is in assignment 5. Okay, question 9 to question 10. So let me go to assignment 5. Is it assignment 5? Assignment 5. Question 9 and 10. Okay, question 9 and 10. Okay. Yeah, so the first question is the conceptual question, question 9. So for pure rotation, the determinant of the rate of deformation tensor. So you have to find out the determinant of rate of deformation tensor D for pure rotation. Okay. So this D will be equal to the identity tensor for pure rotation. Is it clear? Can you see?
Yes, sir.
So when you take determinant of D, which means you have to take the determinant of identity tensor D I, which is nothing but equal to 1. Okay, so that would be the answer. Because it's a pure rotation, there is no deformation going on. Okay, so this D will be equal to I.
Okay, sir.
Okay, and now coming to question 10. So you have the velocity field of a rigid body about the x3 axis given as v equal to minus omega 1 x2 E1 plus omega 2 x1 E1. Oh, sorry. E2 plus omega 3 E3, where omega is omega 1, omega 2, omega 3 transpose. It denotes a constant angular velocity vector. Then given omega equal to 2 comma 2 comma 0 transpose, the magnitude of the acceleration field you have to determine. Okay. So for the particle which is currently at 1 comma 0 comma. So currently means the spatial coordinates x. Okay. So you have to find out the acceleration. So what you have to use is basically, first you have to find out the velocity gradient tensor, which is nothing but del v by del x. Okay. And from the concept of this material time derivative of spatial quantities, you know that acceleration is given by del v by del t plus L v. Is it clear? This relation must be there in the slides.
Yes, sir.
Okay. So now you can first find out this velocity gradient tensor. So v is given to you. So this is nothing but your 0 minus omega 2 0, omega 2 0 0, and 0 0 0. Okay. So this is your v1, this is v2, and this is v3. Okay. So del v1 by del x1. So this is v1. This is v2. This is v3. So del v1 by del x1, there's no x1 dependency, so that is 0. So del v1 by del x2 is, sorry, this is minus omega 2. No. This should be minus omega. I think there is some issue over here. Yeah. So basically there's some issue over here. I think there's some typo, but are you getting the concept how to calculate?
Yes, sir.
Yeah. So you first find out the velocity gradient tensor, and then you use this relation over here. Okay. The acceleration is so when you have to find out the acceleration, use this relation. V is given, x is given. So at this x, you can calculate v. At this x, you can calculate the velocity gradient tensor, and del v by del t also. So there's no time dependency in velocity. So basically del v by del t will come out to be 0 vector. So all you need to do is A will be equal to L times V. Okay. Is it clear?
Yes, sir.
Yeah. So this is omega 1i. Okay. So that is mistake that I did. Okay. So now going to what happened? Yeah, I think I have to add more slides. Yeah. Yeah. So this is assignment 6. Question 13 to question 15. Okay, so assignment 6, question 13 to question 15. Yeah, so this assignment question again is what we discussed already, right? So given sigma is 2, 6, minus 6, 6, 3, 0, minus 6, 0, 1. And then F is, so this is the stress tensor at a point P. And through the same point P, you have a surface which is given by x1 plus 2x2 plus 2x3 minus 2. So you already have a surface which is passing through this point. Okay. So first thing you can calculate the unit normal. So that should be gradient of f divided by the norm of the gradient of f. Okay. So you can find out the normal. Then you can use the Cauchy's rule. That is T equal to sigma n. So you can find out the traction vector T. Once you have traction vector, you can take a projection and find out the normal vector. So T dot n into n. And once you have the normal vector, so this shear vector, okay, so normal plus shear is equal to T, which implies that the shear is T minus Tn. So Tn you calculated, T you calculated here, so you can find out the shear. So once you have found out this, you can find out the magnitude. Okay. So this follows what we discussed a few slides back. Okay, you can find out the magnitude of the normal, and the shear vectors, and also the traction vector. Okay, so is it clear? I think there are. After this, I think I did not get any questions. Let me check the chat box. Yeah. So if there is any question, you can ask right now. Or should I go to the last part of your doubt, which is some reference books you wanted to ask, right?
Yes, sir.
Which are available easily for this fundamental application on numericals, where we can solve numerical on basis for that. Okay, so basically, you are looking for some books, right?
Yes, sir.
Okay, so I mean, are you looking for some books in the continuum mechanics domain or in the numerical domain?
In numerical domain.
Okay, numerical domain. I mean, one book which I followed in this course, it's there is this book by Bonnet, Gill, and Wood. Okay, so it's a non-linear continuum mechanics for finite element analysis. That's the second edition, Cambridge University Press, 2016. And the same authors also have the worked out example. Okay. A separate book on worked out examples. So these two books are where you'll find a lot of the same theory, what I discussed. However, in the slides, you will find a detailed derivation of all those equations, which are not there in these books in that detail. And you can find beyond that, I'll not write, but there is a nonlinear finite elements for continua and structures by Belichko, Liu, Moran, and El Khodri. That is the second edition Wiley 2014 book. Okay, so should I write?
No, it's fine, sir.
Okay. So that is one book. There is a nonlinear FEM book by Namho Kim. Okay, that came out Springer book 2015. So that book has a lot of this theory and numericals from the finite element side, nonlinear finite element side. Okay, but if you want something with computational continuum mechanics, so this is the book. Also, a very good book is the Gerard A. Holzapfel. Do you know this book, Holzapfel? Nonlinear solid mechanics.
Yes, sir.
Okay, so nonlinear solid mechanics, a continuum approach. So that's John Wiley and Sons, 2000 edition. So this book also has some problems, some numerical problems you'll find. So are you looking for numerical examples in continuum mechanics? Or
yes, sir. I'm looking for that part.
okay, that part. So there is a very good book on principles of continuum mechanics by J.N. Reddy. So he has a lot of books. He gives a lot of examples there. So you can refer to that. Then you have a book by, let me So solved, you are looking basically where there are solved examples, right? A lot of solved examples.
Yes.
Yeah. So there is Lai, Rubin, and Krempel. You know this book?
I didn't hear about this book.
Lai, Rubin, and Krempel. That's introduction to continuum mechanics. They also have a lot of, so that is Butterworth, Feynman, second, oh, sorry, fourth edition, 2015. Okay. And then this book is there. Then Alan F. Bauer. So he's from, I think, this university, Brown University. So he has this book, Applied Mechanics of Solids, CRC Press, 2010. So you can go online and type solidmechanics.org or something, Alan Bauer. So he has a dedicated website. So the entire book is available as chapters, and many finite element codes are given in his website. Okay.
Yes, sir.
So you can find this over here. So let me see. So these are some of the book I refer. Yeah. So from the classical side, there is one book by Chadwick. You know this? Peter Chadwick.
No.
So this is Continuum Mechanics, Concise Theory and Problems. Okay. So it comes from the Dover publication. So as the name suggests, so theory is concise, but it has a lot of problems. Okay. So this you can refer to. And off late, there is one more book. Yeah. So there is one more book which has come in 2019. It's Continuum Mechanics Modeling of Material Behavior by Martin H. Sad. Okay, so that's from the Academic Press, 2019. So he also has a lot of this numerical type of examples. Okay. Also, there is this book by Massey and Massey. That's a very classic text. Continuum Mechanics for Engineers. So these are some of the books that I'm referring to. These have a lot of numerical examples. Okay, 1999. So they have a recent fourth edition also. I have that fourth edition, which I bought. So it also has the same lot of numerical examples. So there are two Indian authors. I'm just forgetting their name. Maybe I'll send by email. So they also have a lot of example, but they are out of print books. So you may have to look it for some website where you can buy second-hand something, eBay books, something where you can buy that. Okay. So, but if you want, I will suggest that this Bonnet and Wood is one book that you can refer to as a first go. Okay. Is it fine?
Yes, sir.
Okay. So as we are coming towards the end, are there more questions?
No, sir.
Okay. Yeah. So there is Dr. Anil Kumar is there. So you have any question? You can type in the chat box if you have. Anyway, you can always send me email. I'll reply to those emails. Okay, so Pooja, I'll send you the name of the other two books, Indian author books. So those books also have a lot of this numerical problems to try.
Yes, sir.
Okay. Okay.
Sir, I'm having one question.
Yes.
Like there is the coming module for week 8 and week 9. It is for hyperelasticity.
Yes,
So
yes.
is it like necessary that we need to attend this kinematics and kinetics and then only we can move to hyperelasticity?
Without kinematics and kinetics, it's not possible to understand hyperelasticity. Basically, that's a continuum mechanics course. Hyperelasticity is a special case of, constitutive relation.
Yeah.
So, yeah. So unless until you know these concepts, it's not possible.
Okay. Okay. Fine.
Yeah.
Thank you, sir.
Okay. 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 So if there are no more questions, then can we wind up for today?
Yes, sir.
Okay. Okay, then. Thank you very much. Thank you.